Okay, so this diagram shows us horse evolution over time. We have 60 million years ago, 40 million years ago, 25, 7, and 3 million years ago. So further back in time, it looked like this, and as we went forward in time, the appearance of the horse changed. It got larger, and it became more like the horse that we know of today. So this data in the diagram, what is it evidence of? Did the new species suddenly appear? A new species of horse, did it suddenly appear? No, this is not suddenly. This is over tens of millions of years that we had these small changes add up to become what we know today. So there's nothing sudden about that. Horses slowly developed over time. Well, yeah, I mean, over 60 million years. By the way, this is when dinosaurs were on their way out. So these early ancestors of horses were running around at the same time the dinosaurs were. Isn't that silly? Horses have similar stages of rapid embryo development. We don't know what their embryos look like by this picture, so we can't say. That might be a true statement. However, we can't tell that from the picture, so we can't choose that one. Horses have a common ancestry with other hoofed animals. Again, we have no way of comparing horses to other hoofed animals. So the answer to this one is probably G, right? Now they slowly developed over time. Over 20 million years, another 15 million, another 18 million, another 15 million. So every almost 20 million years or so, you had new species come around. That's a very slow, gradual change. Okay, which statement is best supported by the data? So we have the number of reptile taxa, which just means like the number of reptile species, okay? The number of reptiles living. We have the Permian period, Triassic, Jurassic. This was all dinosaur stuff, right? And then Cretaceous. So the dinosaurs kind of were on there. Well, Cretaceous, there were still dinosaurs around, but toward the end, okay? So basically, my point is that look at the number of species. The taller the bar, the more species of animals there were during that period. What do you notice about this period here in the Jurassic period? The early period, Jurassic period, we had a ton of lizards, or reptiles, I'm sorry, dinosaurs basically. And then late Jurassic, we had a lot less. What do you guys think happened? Y'all know how the dinosaurs went out, right? The prevailing theory, the asteroid, right? So what do you think happened between the early Jurassic and the late Jurassic? Yep, that's what happened. That's why it went from this many down to this many. So what statement is best supported by the data? Competition for food and shelter was very low during the Triassic period. Well, we can't tell that from the graph, okay? In the Triassic period, the numbers go from low to high, but we don't know if there was low competition. We don't know. A great extinction occurred during the Jurassic period. Yeah, obviously, right? Early to late Jurassic period, somewhere in the middle, we went from a lot down to very few. That's the asteroid. That's what happened. That's when that happened. Which, by the way, they're pretty sure they found the impact site of that asteroid. And they always thought that it was in this place, but then they found even more. They're like, recently, and they're like, okay, yeah, no, this is definitely probably it. Mollusks in the fossil record, okay? So once again, this is the fossil record. Remember how I told you it's layers on top of layers on top of layers? And as you go down, you go further back in time. So if you look at the layers, you see that there are big big mollusks, which are like oysters and clams and stuff like that. And there's a sharp line where they're small after that, okay? So very early on, they're all small. Stasis means stable. And then a rapid change happened here, and then now they're all big after that. So they were small, something happened, and now they're big. So how can we best explain that? Which answer choice basically just describes exactly what they're showing you here? Let's see, H, the mollusks were not well adapted to their environment. The length of the mollusk's shells changed gradually over time. So it didn't change gradually over time because this tells you rapid change, right? So rapid change is not a gradual change over time. Like all the shells were small, something happened, and then quickly those are all gone, and now the only ones left are big ones. So let's start with F. The mollusks were well adapted to their stable environment. Stasis means stable, so yes. A large sudden change occurred in their environment. A sudden change or rapid change happened, yes. After the change, the mollusks with the bigger shells were better adapted for the new environment. Yes, that's why there's only large. So something happened, I don't know what it was, but something happened to where only the large shell ones were able to survive. And whatever that change was, it happened quickly. So yes, that is the answer, right? F is the answer. Okay, we have a cladogram here. Which discovery would challenge the validity of this cladogram? So what they're saying is that we have this, remember how to read the cladogram? This is the beginning of time, this is the end of time, or today, at the end of time, this is today. And everywhere you have an intersection, it tells you how long ago it was, about 425 million years ago. It tells you what happened there. So about 425 million years ago, this happened. And then later on, this happened, these guys came around, and then later on, these guys came around, so on and so forth. Let's go one by one and rule them out. A large aquatic vascular plant about 200 million years old. Remember, we're looking for something that doesn't fit this graph we're looking at. We're looking at something that does not match. A large aquatic vascular plant, 200 million years old. So let's go back to 200 million years. Well, this is 380 million years, so 200 million years is going to be somewhere like close to today. Okay, it's going to be between here and today. So a large aquatic vascular plant would fit here because vascular plants came around way before that, way back here. A species of algae that has existed for less than 1 million years. Where are algae? Here's algae. Algae have existed since basically the beginning of time. So if you found one that was less than 1 million years old and they're still around today, that's not weird, right? So that's not it. A moss species that has existed less than 380 million years. So here's 380 million years ago. Is it weird to find a moss? Well, moss is still around today, right? So it's not weird to find moss that's less than 380 million years old because it's still here today. Of course it was around. It wouldn't be strange to see it greater than 380 maybe, but not less than. A fossil of a fern more than 425 million years old. Here's 425 million years ago right here. At this point, this is 425 million years ago. Would it be weird to find a fern, which is a vascular plant that didn't come around until, according to this graph, way up here? Would it be weird to see one of these vascular plants way back here? Yes, it would be, right? It would not match this graph. Because a fern is a vascular land plant. And it doesn't say vascular tissue even evolved until 400, here. So it wouldn't have matched here. Okay. Which of the following conclusions is supported by this information? What information do we have? Well, let's read it. After examining the fossil record, scientists have determined that scorpions today are much smaller than their extinct ancestors. This is going to give you nightmares. Think about this. For example, this species, I'm not even going to try to pronounce it, it doesn't matter. It's just a species of scorpion. A giant scorpion species that lived 255 million to 460 million years ago was 2.5 meters long. Do you know how long 2.5 meters is? That's 8 feet. Can you imagine an 8-foot scorpion? Yes. They found fossils of them that used to exist. Let that haunt your dreams. Small scorpions haunt my dreams. Those things terrify me. I can't imagine an 8-foot one. Holy crap. So anyway, they found they used to be 8 feet long, and now they're this big. Obviously, they're smaller, right? They didn't get bigger over time. They got smaller over time. So which of the following conclusions matches what I just said? They got smaller over time. This is very simple. Scorpions living today have increased their numbers. Well, we don't, maybe, but that's not what we're talking about. We're not talking about numbers, we're talking about size. Let's see, H. Daniel says H. Scorpions have changed as a result of natural selection. Probably, possible. Let's read the other ones just to be safe. Scorpions in the fossil record are smaller than their descendants are. No, descendants are the younger ones, the ones today. Those are not, the old ones are not smaller than the ones today. Scorpions do not appear in their original state in the fossil record. Okay, so here's the thing. J is true because they do not appear in their original state. Actually, wait. It is H. Yeah. Well, it could be H or J. Honestly, this is kind of a tough one because they're both true. They did change as a result of natural selection, but they're also not, they're obviously not still 8 feet long. So I'll have to get back to you on that one. But just for the sake, because the answer key says J, go ahead and put J, but just know that H is also probably true. So Daniel, you're not wrong. I'm not saying you're wrong, but let's just pick J because that's what the answer key says. All right. The fossil record for an organism that has undergone stabilizing selection for millions of years will most likely look like A. All right. I have to hurry. Okay. How many more of these do I have? Oh, geez. Okay. All right. That one's A. It's stable. The species was stable over a long period of time, so you're probably going to find one that looks the same through multiple layers of rock. Okay. It's not going to be, there's not going to be a big change. It's not going to be like it's 8-foot scorpion, and then it's a 1-foot scorpion, like very quickly. Okay. It's not going to be like that. If it's stable, that means it's the same thing for a long period of time. So you're going to find the same fossils throughout many layers of rock. Okay. Which statement best supported by the information in this graph? The blue line is one species. The red line is another species. This blue line species, which is this one, don't worry about what it is. Just know it's the one that's represented by the blue line. This is 450 million years ago. This is 300 million years ago. This is how many different species there were. The higher it is, the more different kinds of species there were. You can see that there was this many species, 450, this many, 300. It's about the same. The number of species for the blue line is about the same. And that is for 150 million years. And that's what B says. From 450 million years ago to 300 million years ago, the environment for this species stayed the same, the blue one, because the number of species stayed about the same. So their environment must have been very stable. And last one, We have layers of rock here that are coated by pattern. Species A is in this one here with dashes on it. Species B is in this one with the dots on it. Which one is lower, further down? Species B, the one with the dots, is further down. So which one's older? Species B. So species B was first, and then over time it turned into species A. What does this tell us? It probably tells us that the environment changed and species A was better suited for it. That's why species B died out here. And later on, you still find species A later on after that. Some change happened. A was better suited and it lived longer, and that's why you see it there. All right. Sorry, I went all the way to the bell.